Okay. All right. So today we'll talk about random sums and random graphs. So here's the usual review stuff. So what we've done so far, the first day was about linear of expectation and some applications to three stack, quick sort, and by now you've done quick select. Uh, then we did heavy hitters, which was your first exposure, for example, to hash functions, limited randomness hash functions, and also some standard tricks like amplification just by repetition. And then we did linear probing. That was like a relatively sophisticated hash table analysis with sort of some generalizations from that previous lecture, like k-wise independence or a stronger inequality, the Markov's inequality. And then last time we did this min-cut algorithm, this idea of randomly contracting edges, seeing what's left, and with some probability actually outputting the minimum cut, had the interesting consequence of showing there's a limited number of minimum cuts. And then we could do a little bit better by instead of repeating all the way from the beginning, we kind of reset partway through. More precisely, we kind of reset exactly when the probability of failure hits roughly 1/2, because that sort of fit nicely with this analysis, which was this kind of Galton-Watson tree from kind of population stuff. Okay, we're actually going to see that again today. Okay, so what's today about? So we're going to talk about a really cool kind of topic called the giant component that appears in random graphs. But a big thing we're going to learn about is well, the name would be the Chernoff bound, but it's going to be our first real concentration inequality. Yeah, and then it's going to seem a little exotic the first time we see it, but we're going to use it like again and again and again and again, so it will become more comfortable. So if it feels weird today, just hope it'll get a little bit better because we'll get a lot of practice with that particular kind of calculation. Okay, so let me start with this concentration stuff. Okay, so let's say I flip 100 coins and 50 of them come up heads. Okay, should you be surprised? No, why no? It's sort of the most likely individual number. I think this is like what's the name for this? Is like that useless name? Uh, no, it's not. Well, but it's the mode, right? And there's like a mean, a median, and the mode has like no use. Um, okay, so it's the mode. You could be kind of surprised because it's only an 8% chance of this is happening. Exactly 50. Okay, but okay, here's something more dramatic. If I flip the 100 coins that says 0 comes up heads, should you be surprised? Yeah, right. You should be outraged, because that should of course never happen. The odds of that happening is 1/2 to the 100. Okay. All right. So that much all makes sense. Okay. How about this? You flip 100 coins, and less than equal to 25 comes up heads. Okay. So should you be surprised? Now, there's two ways to look at this. The mode, I guess, is 50, and the average is 50. So 25 and less, each of those are less than half the average. So they're kind of far away from the average. But on the other hand, I'm giving you 26 possibilities. You get all the points for 0, 1, 2, 3, all the way up to 25. Okay, so you expect them to be individually smaller than the 50 number, but you get 26 of them. So uh, the question is, should you be surprised? Or maybe more quantitatively, what do you guess the probability might be? Anyone wants to venture a guess? What are the odds that you get at most 25 out of 100 coin tosses? Fairly low number. Okay. So like as a number between 0 and 1. 10 to the negative what? Well, I don't know. Well, you don't have to do it. I just want to know what you think. I just 10 to the negative 20. Okay. Uh, sorry. 0.0038. Okay. Awfully specific. Huh? 10 to the negative 5. So these are all as probabilities between 0 and 1. So that would be 10 to the negative 3%, I guess. Yeah. Okay, well, hopefully you all thought about it a little bit. The answer is, I guess, 2.8 times 10 to the negative 7. Okay, so 10 to the negative 5%. So still way less than 1% or something, right? So that means like it really adds up to a very small amount. That whole section from 0 to 25 is very, very small. Not quite 10 to the negative 20, but very small. Okay. All right, how about this one? Flip 10 coins, and at most 4 of them come up heads. What are roughly the odds, or should you be surprised? Say no. Anyone want to venture a guess? Just for fun. There's no wrong answer. Okay, that might not be the right answer because it should probably be less than 50%. Uh, yeah, these are normal coins and they're independent coins. And yeah, even though it's Javier Bardem and he seems awfully scary, this is a fair coin. So I guess I punched this in. It's 37.7% apparently. Okay, so keep that in mind. Now, suppose you flip 1,000 coins and at most 40% comes up heads. So same proportion as before. So that's 400 heads. Should you be surprised, or quantitatively, what do you guess the number might be? So the exact same proportions as before, same percentage. All right, 10 to the negative 9. Anyone else? 0.0037. Huh? 377. Any other? Okay, but I guess you guys are all expecting this to be much smaller, and that is going to be the theme. So although the proportion is the same, 10 to the negative 9 was closest. Uh, so it's roughly 10 to the negative 10. Okay. So well, when you look at these two, right, it's the same proportion. All that changed the number of coin tosses, and this is like completely different, right? 37.7, a third of the time, compared to you're never going to see this. Okay, you're going to get struck by lightning first. Okay, so scale matters, and that's really the point of emphasis. Okay, so one way to model this is the following setup. Suppose I have a bunch of random independent variables. Okay, and they're bounded. What really matters is that they're bounded. Here I've bounded them to be between 0 and 1. If it goes between like 0 and 10, you scale down by a factor of 10. Okay, and I'm going to let mu denote the average sum. Okay, and what I'm interested in is what is the probability that the sum comes out close to the expectation. Okay, and in particular, multiplicatively close. What are the odds I'm within 10% of the expectation? That would be the what we no, I guess what we just did would be 20%, right? Because 20% of 50 will get you down to 40. Okay, so I'm interested in kind of what are the odds I'm within 20% of the average, 10% of the average, whatever. But it's a multiplicative factor, not like off by 2 or 3 additively. Okay, and so concentration phenomena says that when these things are independent, they're just kind of individually small contributions. The odds of deviating from the mean is going to be exponentially small in the mean. Okay, so it's when we did that 1,000 coin tosses and you got that small number, that was really exponentially small in 500 because 500 was the mean, more so than the 1,000 coin tosses. Okay, so that's the real point. Now there's more precise bounds. Okay, and I'm always a little worried that looking at this is a little distracting from the qualitative idea. So I fix some parameter epsilon between 0 and 1, like 0.1 would be 10%. What are the odds that you're at least 10% away from the average? On the upper side, it'll be, if you are careful, e to the negative like epsilon squared mu over 3. Okay, the real key point is the mu, right? For any fixed epsilon, this is just a constant. You're dividing it by a constant, but it's going down exponentially fast in mu. Okay? And then on the flip side, I say, what are the odds I'm 10 or 20% less? The constants are like a little bit different, which is kind of annoying, but it's not that big a deal. Again, it's going to be exponentially small in the mean. Okay, and it turns out that for small epsilon, you're going to pay epsilon squared here instead of like an epsilon or something like this. And you end up seeing a lot of epsilon squared bounds in various algorithms for this exact reason, but this is secondary, right? The most important thing is that when you have lots of individual independent pieces adding up to a large sum or large whole on average, the odds of deviating from the average plummets exponentially in that average. Okay, so exponential is very strong. Like, we did these algorithms where it's like, what are the odds of getting 10 straight tails? 1 over 2 to the 10. We did amplification like this, right? That was exponentially small. You're getting the same thing, but with a weaker constant. It won't be 2 to the negative 10. It'll be something, depending on epsilon. Okay, but it's plummeting. It's plummeting. Okay, so this lecture is well, we're going to use this phenomenon many different ways, but this lecture is about a particular situation where this phenomenon has a big effect. Okay, and it's pretty cool. It's not really an algorithm. It's like the one lecture. It's not really an algorithm, but it's still cool, and it's on graphs, so hopefully, that's permissible. Okay, so let me explain the model. Uh, these are called Erosh-Renyi graphs because Erosh and Renyi had a series of papers where they're analyzing random graphs. Okay, and they were inspired by previous work by a guy named Ramsey, Frank Plumpton Ramsey. He has a great name, and who was trying to answer the same question that Turing eventually answered, but Ramsey gave up partial solution based on probabilistic techniques. But okay, this graph model, in any case, you start with n vertices, and think of n as being large, and we're interested in asymptotic behavior as n gets large. And then for every pair of vertices, I'm going to independently generate an edge with some fixed probability, p. And you get a random kind of symmetric-y graph that way. Okay. And so then you start asking, the basic question you want to ask is what does such a graph look like? Especially as a function of p. And mathematicians have a million questions, right? Like how many colors do you need to color the graph? Is there large clicks? Is there this? Is there that? Okay, there's 100 questions you can ask. But one thing that Erdos and Rennie kind of keyed in on is this very cool idea. This is a very random graph, right? Completely random. Completely random. But does it consistently have certain properties? Okay, so take, kind of the most random graph I can think of. Are there consistent things I can say, it's always like this, it's always like that? And that's because such a thing would be quite counterintuitive. Okay, so, okay. So here's what we're going to show today. Okay, so suppose, I don't know if this is hard to read. So, okay, so suppose that p was some constant divided by n. So that means the average degree is basically c because there's n minus one other vertices. Okay, so if everyone gets sampled was probably c over n. Maybe I should have wrote c over n minus 1 to make it a little cleaner. Okay, but c will be the average degree of every vertex. Okay, so if it's like 2 over n, then multiplied by roughly n neighbors, you should expect 2 neighbors. Okay, and what we're interested in is what's the difference between c big and c small or something, and if there's anything going on. Okay, all right, so what they found is this. If c is any constant bigger than 1, c is 1.000001, and as n tends large, you're going to get exactly one connected component with order n vertices. Okay, exactly one connected component with, half the vertices or something in it. And then all the other connected components are going to have at most log n vertices. Okay. So as soon as this becomes anything bigger than one, you get one giant component with a bunch of small ones. And if it's any constant less than 1.99999, all the connected components will be small. They'll all have at most log n vertices. Okay. So suddenly when you go from 0.9999999 to 1.00001, you go from a graph with no real significant components to one giant component, right? And the drama is kind of, the point is that you change this c by a small value, you would think, and you get a qualitatively completely different graph. Okay? So this is called a threshold phenomena. And actually, I was talking to David Gleich, and he told me when he was your age, he put together this demo, which you could find online. So red is supposed to be the giant component at the given point in time, and he paused it right when the average degree hit 1. So we can wait for it to restart, I guess. Eventually, it has to. Okay, so there's the largest component. But as you start to approach, now you have a giant component, and as you get bigger, it's going to fill in. Uh, okay, it's exciting. All right. Okay, that's the idea. Okay. Um, so I wanted to mention. So this is an example of a threshold phenomena, and this might seem a little artificial, like a math problem. To some extent, it is, but actually, it occurs. This comes up quite a lot in things like physics and other real world models, where you get kind of threshold phenomena. So I don't know, there might be physicists or people with a broader background in this room, but can anyone think of an example that might behave like this, or where you might get other threshold phenomena? Yeah. Yeah, so I think this will probably come up with population stuff. Yeah, so this is threshold phenomena is another name for a phase change. So what are some examples of phase changes? Water to ice, right? So when you hit 0 Celsius, it really goes to ice immediately. And it doesn't start becoming ice at like 1 degree Celsius, right? And what's happening, the molecules kind of lock up with each other and you have this. Yeah, so that's one example. Any others? There's one that was like kind of very relevant to our lives in the last 10 years. Yeah, so epidemiology. So they also call it I think reproductive rate or something like this. But the basic thing is if someone gets sick, how many healthy individuals do they expect to infect? Yeah, and their models are going to be more detailed than quite this simple model. But in general, all their models have this explosive behavior, right? It's very hard to model these pandemics because a small change in that kind of basic average degree can lead to kind of explosive, at least in the simulations. Okay, so that's one reason why these epidemiologists and stuff are so sensitive. Why small things make a big difference, and so forth. Okay, but there's lots of examples, certainly in physics, etc. Okay, so good, good. This will just be a clean. Yeah, will be sort of a clean example. Yeah, yeah. You can think of it as a fully connected graph. You could think of starting with a fully connected graph and then dropping all the edges as probability 1 minus p. They think of it as starting as an empty graph, and every single one gets sampled with probability p. Yeah, but all connections are possible. We'll be looking at the degree close to 1, so you should imagine a fairly sparse graph. The degree is close to 1, because that's the interesting point of sensitivity. Okay, good. Right. Okay, so we're going to focus on the case where the average degree is slightly bigger than 1, and then we leave for homework slightly less than 1, which will have some similar things, but some things will have to flip. Okay. And so we're going to break it down into 3 parts. The first part is maybe the most complicated looking. It's called the gap theorem. So I'm going to let p equal to 1 plus epsilon over n. Maybe I should have written n minus 1, but I won't worry too much about it. Okay. Uh, so in particular, I'm thinking of something a little bit bigger than 1 plus epsilon. Okay. And so what we're going to show is a certain like dichotomy theorem. Okay. We're going to show that all the connected components are either pretty small, a size at most log n over epsilon squared, that'll be the dependence on epsilon, or really big, at least epsilon times n. Okay? And there'll be nothing in between. That's the real key point of this theorem. Okay, so it doesn't show that there exists a big component, but it shows there's kind of no middle components, middle-sized components. Okay, the second part will be the existence of a large component. So we'll show there's at least one of these things that have size at least epsilon times n. And then lastly, the uniqueness of the large component. There's only going to be one. That's actually going to be the quickest one. Okay. That approach makes sense. Theorem, I mean, it should be kind of a new perspective for many people. So, all right. Okay. All right. So let's do that gap theorem first. So, right, the average degree is like 1 plus epsilon. And what we're going to do is we're going to focus on a particular vertex V in our analysis and see how big is the connected component of V. Okay, we want to show it's either small or really, really big. So, okay, so we're going to fix V. And I guess I'm writing C of V, denote the connected component of V, the random realization of the connected component of V. Okay. And okay, so what we really want to analyze is the size of CV. And we're going to follow an analysis actually by Richard Karp, many years later. But so to analyze the connected component, we're going to imagine kind of starting from V and gradually figuring out the neighbors and connected components as if you're running like DFS or BFS. Okay, so we're going to imagine we're running a search algorithm. Exactly which search isn't that important, but you're going to start at V and kind of grow out. And along the way, you'll like reveal edges. You start at V and you say, what's my neighbors? I find out some neighbors, but I don't know the neighbors yet. And then I'll go explore a new vertex, unmarked vertex. So I'm going to kind of delay finding out the edges. That'll be helpful in the analysis. Okay, so the model originally was, oh, all those edges are sampled, but it's helpful in the analysis to kind of change it as if the edges are revealed online as we explore them. Okay. All right, so that's going to be the idea. So here then, let me set up the notation for us. Okay, so yeah, it's sort of like marked and unmarked vertices. We're going to let the set A at any point in time kind of denote the set of vertices I already know are connected to V as I'm exploring. So at the beginning, A will just consist of V. And B will be the set of vertices I've explored. I've kind of marked. I've found out and revealed all of their neighboring edges. And so the algorithm is going to be like, well, for I equals 1, 2, 3, 4, 5. While there's some vertex that I know is connected to V, but I haven't explored yet, I'm going to, explore that vertex. I'll add all of its neighbors to A, which might be none. It could have no neighbors. And then I'm going to add it to my marked set. Okay, so nothing special. Okay, I'm not too concerned with the order out of A that I kind of draw things. Okay, good. And for us in our analysis, it's going to be helpful to kind of index it by rounds. So A1 will be after one round, B1 will be after one round, A2, A3, A4 after 2 rounds, 3 rounds, 4 rounds. So originally A0 will only consist of V, and B0 will be empty because we haven't even explored V yet. And so VI will be the vertex in the ith round. Okay, so I'm just going to subscript everything. Okay. All right, so that's our setup. Okay, And now, okay, all right. So maybe just to set the scene, at some level, again, we find ourselves trying to analyze something. On one hand, it seems kind of simple, like it's a simple algorithm, but the randomness is like makes it chaotic, right? It's sort of like quicksort. Before you had ever analyzed quicksort, it's not quite clear how to approach it. Okay. So what we're gonna do is we're gonna take some baby steps and just put some observations together, and we're gonna try to clean up, sort of this dynamic, chaotic algorithm into something that we can really rigorously kind of pull out something clean. Okay, so all right, so here's the first observation. So one issue is that okay, I sort of have these vertices. I know I'm connected A, and then I have B, and then I kind of want to just focus on A. Okay, now A is the set of vertices that I know are connected after 10 rounds, 11 rounds, 12 rounds. Okay. And the algorithm formally terminates when B is fully equal to A. Okay. But maybe another way to think about it, right? If I finished in 10 rounds, that means after 10 rounds, I've also figured out 10 vertices that are connected to V, including V, and I didn't find any more. Okay. If I had 11, I would have one left over, right? So this is because BI, the size of BI is always equal to I, right? That means that I terminate only if BI is equal to AI. And that's if and only if, oh, and you also know that BI is a subset of AI. If you wanted to do this slowly and formally. So B is equal to AI if and only if AI is equal to I. Okay, just baby observations. It's not actually quite clear why this is useful for us yet, but, but bear with me. Okay, so that's the first observation. That at some level, that I don't have to terminate based on B. I could have terminated just by observing the cardinality of A. Okay. So here's the second observation. Okay. So I'm just kind of focusing in on A, right? At some level, so in the algorithm, right? The algorithm is kind of very specific. Actually, how about this? I'm going to read out the statement and then let someone fill in the reasoning. So the claim is that if I'm just looking at the AI is going from A10 to A11, I can think of that as just sampling all the vertices that aren't in A10, each with probability P, and adding it to A11. Whereas the algorithm is more specific. The algorithm picks a vertex, explores its neighbors. But I'm saying, but I could have equivalently just said that A11 is obtained from A10 just by sampling everyone who's not in A10, sampling from everyone who's not in A10 with that probability P. Okay, so this is kind of simpler in some ways because it's not worrying about some particular vertex. So that's the claim. So now my question is why? Yeah. Yeah, I think that's basically right. There's maybe one kind of key point I want to focusing on. That's also true. The edges I'm not revealing. But maybe the point I want to drive at in particular is that, what we're kind of removing from the description is the particular vertex that's we're looking at the neighbors, right? This observation is sort of saying it doesn't matter which vertex, but why does it not matter which vertex? So any vertex, right? I mean, it all kind of agrees with everything that was said. No matter what I pick for that 11th vertex, sort of its distribution of neighbors, right? Which edges it will be the same no matter which vertex I pick. They all have that same distribution of all edges with probability P. So it didn't really matter which vertex from this, slow revealing point of view, it didn't matter which vertex I picked for A11 because that information, there's nothing to distinguish them anyway. Okay. All right, so that's sort of the idea, but the key point is that it didn't matter which vertex. But one thing nice about these two observations, which at some level they don't seem to say much, except uh, they're going to simplify our analysis, right? Because I'm no longer really worrying about B, and I'm not really worrying about the vertex that I pick anymore, right? Now I'm basically just studying this set AI, right? I'm focusing on the cardinality of AI to see when the process ends, and to get A11 from A10, I just sample, right? So at some level, the whole search algorithm, everything kind of graphical about it, has suddenly been abstracted out. Now I'm just looking at this kind of sum. Does that make sense? Okay, so sort of this crazy combinatorial nature of graphs has actually been kind of very cleverly been abstracted out. Okay, good. Right. Okay. So now we can analyze sort of this process, and it'll be equivalent where originally I start with uh, a0 is equal to 1, and each round I'm just going to sample, add to AI. Yeah, so I'll sample a set Si. So I start with A0 and I sample S1 from all the vertices except for my starting vertex. And then I'll add it to it and I'll get my set A1. And I check to see if A1 has more than one vertex. If A1 only has one vertex, I'm done. Then I'm moving on to round two. So in round two, I'm going to sample the set S2, which is going to sample from everyone except for those already in A1 with some fixed probability. And then I'll get my set A2. I'll check to see if A2 is at least 2. If so, I keep going. If not, I'm done. Okay. There's almost no graph left. We can keep the metaphor running because it's easy to discuss, but analytically simpler now. Okay, good. So let's look at these sets, these AI sets, right? Actually, let's look at their cardinality in particular. We just start with A1. So A0 is just that one vertex we start with. So there's nothing interesting there. What is the distribution of A1? Sorry? Yeah, yeah. So like for example, what's the expected size of A1? Yeah, so for example, the expected value of size of A1, I guess I wish I had kind of set up the notation a little more cleanly. Uh, but you'll get, p times like n minus one or something, right? But really, A1 except, or maybe it'd be better if I just wrote A1 minus one because there'll always be one to start with. Okay. Basically, everyone is a coin that flips heads with probability p, everyone else. Okay. All right. So what about A2? At least if I exclude the first one, which is always there. What does the distribution of size of A2 minus 1 look like? Let's just assume we keep going. So in other words, it is true that in this process will halt when AI, A10 is equal to 10. But you can imagine covering this up and just letting it run, right? And then studying the AIs and then afterwards looking back to see if it halted. So imagine you're not worried about the halting. And you just want to understand, like, how big are these sets if they just kind of kept running, kept sampling? Okay. So what is the distribution? What does A2 look like? So A2 is 2 rounds. Yeah. Sorry. P times n minus 2. Okay. So why P times n minus 2? Okay. But one thing to keep in mind is that so in that A1 round, so I guess you get an n minus 2 because you got the second vertex and then you've looked at everyone's neighbors, right? So the 2 is the 2 vertices you have so far. But A1 may have gotten more than one vertex for you. Yeah. P times what? Okay, okay. We could do something like P times n minus size of a one, minus one or some plus one, I guess. Uh, and that would sort of be like conditional on finding out a1. But I want to even think about this unconditionally. Uh, look at some other vertex. Yeah, yeah. So look at another vertex. What are the odds that it's not in A2? So for some other vertex, the probability that X is not in A2, so non-starting vertex, right? Well, you have to flip tails twice. Each round it failed, right? So you'll get 1 minus p squared. Okay? So that means that your set A2 minus 1, so I'm excluding that first starting vertex that's always there. This is going to look like number of heads with, n minus 1 coin tosses, and the probability of heads is 1 minus 1 minus p squared. Okay, because it's probably 1 minus p squared, you lose both rounds and you don't get included. Okay. All right. So based on, yeah. Yeah. So expected number is definitely going up. It's close to 1. It's going to get even higher. Okay. So yes, that's the right idea. So first of all, A3. Uh, I guess you all see the pattern maybe. So for A3, you'll get something similar. So sort of this part sort of looks the same. So what changes? Yeah, so this part will become 1 minus 1 minus p cubed, right? Because that means in 3 straight rounds, you didn't get any edge to the existing thing. And in general, if you were looking at the ith round, you get something similar. Uh, only this will become 1 minus 1 minus p to the I. Okay. But this is very nice, right? Because originally we're looking at like you're doing breadth first search, depth first search, or random graph, and you're taking all these weird turns. And now you're like, okay, I'm just flipping coins, right? Each round is a random sum. Yeah. Yeah, yeah. So I'm sorry. So maybe I should parse what I wrote slowly. Uh, you know, the cardinality of A2 minus 1 is always going to be equal to this kind of, it's going to be distributed like if I had a coin, if I had n minus 1 coins and they flipped heads was probably 1 minus 1 minus p squared, the total number of heads I get, that distribution, that random distribution is going to be the same distribution as A2 minus 1. So this would just kind of parameterizing the distribution. The expected value then would be this probability times n minus 1. Okay, so good. Okay, so I guess the first claim, okay, is that if I'm looking at I, not too big, like up to epsilon n over 4, beyond that point, the calculations get a little messier. Uh, the expected size should be at least 1 plus epsilon I or something. Okay, so how do we do that? Maybe there should be a divided by 2, but we'll see. Well, we can do what we just did, right? So the expected value of AI, excluding the first one, this is going to look like, okay, so everyone flips heads. It was probably 1 minus p to the I times n minus 1, okay? And p is equal to something like 1 plus epsilon over n. Okay, where should we go from here? Okay, well, let's see. I kind of forget how I did it, but let's just go for something. All right, 1 minus p to the I. This is less than equal to e to the minus pi, because you always have 1 plus x is less than equal to e to the x. And I should point out, p is really small for us, right? Because it's like 1 plus epsilon. And if you actually plot this thing, you know, e to the x will look like this, 1 plus x will look like this. But, at 0, they're exactly equal, and very close to 0, they're really, really close to equal. So you're not giving much up in this inequality. Okay. Okay, so this will be less than equal to e to the minus pi. Okay. Um, oh, is there maybe an easier way to do this? Yeah, okay, we can start plugging in the value of p. You get 1 plus epsilon times I over n, 1 minus this thing times n minus 1. Mm, Okay, sorry, so this thing is at least this. All right, now for negative numbers, you also have this side. I feel like I'm not doing this the coolest way, but we'll see. For somebody has my notes pulled up. So for x less than equal to 0, okay, maybe I should go on a spiel about this. All right, so e to the x, I think you may have seen before, is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the fourth over 4 factorial and so forth, right? So that's the Taylor, that's the polynomial expression. So if we look at this, right, when x is very, very small, okay, so 1 plus x is not that big, it's already pretty small, but x squared over 2 is even smaller because it gets divided by a factor of x, so x is already small, okay? And then that's x cubed over 3 factorial goes even smaller. And x fourth to the 4 over 4 factorial is even smaller, okay? And then you just stare at this, you start saying, okay, well, once x is pretty small, it's mostly 1 plus x, or so mostly 1 plus x squared over 2. They become reasonable approximations with some inequality. You can work out which side is bigger than the other, okay? It happens, what you can do is you can like say, oh, if I'm just comparing 1 plus x and e to the x, at x equals 0, they're the same. And if you take the derivative, right, the derivative of e to the x is x, e to the x, the derivative of 1 plus x is 1. And you'll find that, oh, e to the x is kind of dominating the derivative on one side and underneath the derivative on the other, and that's how you get one inequality. You could play a similar game, and you'll find that e to the x is always at most 1 plus x squared over 2 for x less than equal to 0. Okay. Okay. So if we plug that into here, right? Then I start looking at something like, so I'm using that here, okay? And the one factor is going to cancel out here, so we don't need to mention that. You're going to get 1 plus epsilon I over n minus 1 plus epsilon I over n squared. Okay. I know this is like a bit painful to do, and it might look exotic, except you're going to end up doing this like a gazillion times. So you'll get kind of used to this interpolating with e to the x. Yeah. Divided by 2. Yeah. It probably won't harm us either way. Uh, did I get that? Yes. Okay. So that the plus x squared over 2 became a minus here. Okay. I know my terrible handwriting isn't doing us any favors. Okay. But now let's look at this. So we're only interested in the regime where I is pretty small. Okay, some epsilon fraction of n. Okay, and I think I chose that because that means that okay, uh, that means that something like 1 plus epsilon I over n squared. Uh, so I is at most epsilon n over 4. So you start getting something like 1 plus epsilon squared epsilon I over 4n or something. Okay, sorry, this is a little messy. But all I'm taking is one of these I over n's. Okay, so up here I sort of have this kind of linear term that's a little easier to work with, and then this messy kind of quadratic junk, right? This is sort of my error term. Okay, and I is pretty small relative to n. I is roughly an epsilon fraction of n. So I'm going to drop out one of these i's and cancel it with the n. So I'll get like 1 plus epsilon squared epsilon I n. Okay. I wish I had allocated space better. What can I do? You don't need that anymore. Okay, so what do we sorry, this is so gory. Um so you're gonna get something like 1 plus epsilon minus 1 plus epsilon squared epsilon over 4 I over n times n minus 1. Okay, I feel like it's a little messy. You start to lose the plot a little bit. Okay, so bear with me. Okay, the calculations are messy. You'll get a little bit more used to the nature of this style of thing, but let's look at what's morally going on. I really want to get like 1 plus epsilon-ish I over n, right? My bound is probably not quite right up there. I think that should also be an 8 down here because we have this factor of 2 from before. Okay, but 1 plus epsilon, okay? And then you have something like 1 plus epsilon squared. That's pretty close to 1 for small enough epsilon. We're going to assume epsilon is small enough. Epsilon divided by 8. Okay, so like all that will be, say, at most epsilon over 2. Okay, for sufficiently small epsilon, because that 1 plus epsilon squared will go down to 1. Okay, so you end up with something like 1 plus epsilon over 2 I over n times n minus 1. Okay, I wish I had like done the math a little bit. Okay, I'll cheat more. So I'll write 3 epsilon over 4, which which again will still hold because you're working with epsilon over 8-ish for small enough epsilon. Okay. And so you get n minus 1 times n. That's pretty close to 1, but it's not quite, but I put a 3/4 there. So you'll end up with something like this is at least 1 plus epsilon over 2 times I. Okay, so we really proved this was epsilon over 2. Oops, over 2. Okay, let me take a step back because I feel like I probably threw you off with all the calculations we did. Okay, so we're just kind of working through the expectation, and you got this awkward 1 minus p to the I to work with. Okay, and okay, so the first thing we wanted to do is I just kind of wanted to multiply p and I together because that's a little more meaningful. And we use one inequality to sort of get the p and I next to each other in the exponent. We clean that up a little bit, and then we pull that back out. You know, morally, because p times I is pretty small, okay? So you should expect e to the x to be about 1 plus x. We shouldn't lose much from going 1 plus x to e to the x back down to 1 plus x. You do lose a little bit, and that's represented by this quadratic term. Okay, but as we worked it out, that quadratic term, because you know the x is in fact small compared, is small, right? My handwriting is terrible, but this term is really dominated by this term. Okay, so you still end up with roughly 1 plus epsilon. So it's kind of ugly to do slowly, but there's something kind of clean going on, which is just as long as p times I is pretty close to 0, which it is, if you just kind of take a step back and you look and it is, then you can basically practically go straight from 1 plus, you could basically go straight from 1 minus p to the I to just p times I without much loss. And that would have been easier. Okay. All right. So, and there's some ugliness. Okay. Any questions? Any questions like my bailout as to messing something up? What? Yeah. Yeah, I want to prove that the expected value is a little bit higher than I. Yes. Oh, yeah, yeah, yeah. It's true. So if I can prove that like with very high probability, so in general, like we're trying to show that when the degree is close to, I mean, we're trying to show there's a giant component. And the theorem, the interesting part of the theorem is that as you get even as you get close to 1, there's going to be a giant component with high probability. So if the degree is even higher, then it's even more likely to get a giant component. So the critical regime I want to focus on that's hard to prove is a small epsilon. The larger epsilons, you know, if the small epsilon is true, it's true for a large epsilon. Yeah. And then small epsilon is kind of nicer for the analysis. Okay. Let me make, okay, good. All right. So anyway, black box that. Pretend you never had to suffer that. And let's go back to, okay, so now here's the next claim, right? So what I really want to show is, okay. All right, so this says, okay, our expected value for the size of AI is a little bit bigger than I. Okay, by epsilon factor, maybe there should be an epsilon over 2, but that's not a big deal. Okay, we'll do epsilon because it's cleaner. I cheat a little. Okay, and what I'm kind of worried about, right, is when the search, because I'm trying to hope to get to certain size components. So search ends when the size of AI is equal to I. And so what I want to say is, oh, what are the odds that the size of AI is less than or equal to I? Okay. And our claim is that it's basically exponentially small in I. Okay. But the question is why? Yeah. Yeah, okay, great. So we're going to use, this is where the concentration bounds are going to kick in, right? So now we're in this nice place where the average is slightly bigger than what we're worried about. And now we can take advantage of the fact that when I is big, uh, you're going to be very close to the average. So I think it's already spelled out. Yeah, okay. So what you can do is you can think of AI. AI is the sum over all these vertices of xv, where xv is equal to 1 if the vertex is in AI and 0 otherwise, right? Or if it flipped heads or not, right? And these are all independent. See, one thing very nice, if you had originally kind of thought about the random graphs, the independence gets a little bit awkward to reason about, right? But now that we've gotten it to this point where AI is just distributed the same as these coin tosses, now these indicator variables are independent, okay? And our mu value, mu, which is the expected value of AI, is 1 plus epsilon I, or maybe 1 plus epsilon. Okay, good. So now the probability that AI is less than equal to I, well, I can write this as at most, okay, well, let me write it this way first. First, it will be exactly equal to, uh, okay, something like mu over 1 plus epsilon, right? Because mu is at least 1 plus epsilon times I. And to make this like a little more convenient, I'll maybe give up a factor of 2. And I'll say, okay, what are the odds that it's at most 1 minus epsilon over 2 times mu? That should come out to even bigger than I. Oh, this? Should there be there? Is that what you're saying? Oh, yeah, yeah. There should, but like it's uglier, so I was just leaving it out. Yeah, because the slides were set up. There should have been a factor of 2 all along, but it's not that big a deal. Okay, I can put it there for fun. And then maybe here I'll make this I'll make that a 4 instead of a 2 or something. Okay. But now if I plug this in, right, and I'm looking at just putting the exponent up here, then I'll get something like, so I guess I have epsilon over 4. So e to the negative epsilon over 4 squared mu over 2. Okay, so I guess if I had done things a little more carefully originally, this might be something like e to the negative epsilon squared mu over 32 or something, if I carried that all the way through. Okay. But what really matters is that we've distilled the random process into a random sum. Okay. And then once you get it to this random sum, then you can apply the fact that random sums are very well concentrated when they have a large average. Sums of zeros and ones. Good. Okay. Okay, so now this I think you guys can guess. Remember, our goal is to show that all components have size that pretty small or really big, but nothing in the middle, right? So based on what we've done, my claim is we've effectively shown this, but who wants to kind of connect those dots? Why have I shown that there's no component of size, say square root n? So what happens if I plug in square root n for I? I start getting something like, yeah, it's exponentially small in square root n, right? E to the negative square root n or so. There's some epsilon squared and 16s, but who cares, right? Because we're only worried about large n, right? So in other words, the reason why we can only go up to size epsilon n or something is because I said that I is at most epsilon n over 4. That's as long as our lemmas extend, because that was kind of easier for us to work with. But why log n over epsilon squared? Why did we choose log n over epsilon squared as like the small size from which, yeah. Yeah, so if I plugged in log n over epsilon squared, I guess, in this example times 8 or something, right? Then this will start becoming less than negative 1 over n. Okay, or if I had done 16, then this will become 1 over n squared. If I'm working with those constants up there, right? So if I did log n over epsilon squared, the epsilon squares cancel out, and then e to the negative log n starts to become 1 over n. E to the negative 2 log n becomes 1 over n squared. Okay, so once you get past log n over epsilon squared, that's when concentration starts kicking in, right? Because it's exponentially fast, so you only need log n to get to a regime that's very strong. Yeah, yeah. Keep them on their toes. Okay. So that's what happens. Is now, we can take a union bound over all of the intervals that all the values of I we can deal with. So anything that's between, I guess I put 32 here, and epsilon n over 4 here, right? And each of these will be, 1 over n to the fourth or something. And by the union bound, there's at most n of these. It's a little bit less than n. The odds of any of them failing uh, is 1 over n cubed. Not really sure what this statement means. Uh, okay, one sec. This is like a little bit weird. Okay, so I'll just write AI fails for some I in this range. Will be 1 over n cubed. Okay, so for all those large values with high probability, AI is always going to be healthy. Okay, so if you promise that AI is in the healthy range for this range, that means when you're doing your search algorithm, you either die before you get to 32 log n over epsilon squared. AI is less than something down here because the concentration hasn't kicked in, or you're just home free. This whole stretch AI is going to be bigger than I. Okay, until you get to a happy place. Okay, any questions? I feel like I killed everyone's spirit with some calculations. Okay, so good. So that's how we show there's no medium-sized components. Okay, so let's knock out the last. The last two won't be they're a little more conceptual, so it won't be as calculation heavy. Okay, again, I'll suggest that the calculations, they're kind of ugly the first time. They'll always be ugly, but at least they'll be like, you're ugly. You'll be comfortable with them. Okay. All right. Okay. So now let's talk about why there exists a large component. So all we've shown is that there's no medium-sized components, but now we want to show there's at least one large component, and then we'll show why they're unique. The unique one we can actually knock out real fast. Okay, good. So here's the claim. Again, P is 1 plus epsilon n. So my claim is that if I start at a particular vertex, there'll be like at least a 1 over 10 vertex, 1 over 10 probability we get to 10, a 1 over 11 probability you get to 11, 1 over 12 probability we get to 12, and thus 1 over log n probability we'll get to log n. And once I get to log n, I'm kind of happy, or log n over epsilon squared. Okay, so if this is true, I pick one vertex and I try to get up to log n over epsilon squared, because once I get there, I win. Okay, if I fail, okay, that vertex lost. We throw away log n over epsilon squared vertices that it also was in its component, and I try again with a new vertex. Right, so I'm going to get like n over log n tries to get a giant component, or just to reach that critical threshold where I'm home free. Okay, and each of those succeeds was probably like 1 over log n. So you have like n over log n tries, and you have a 1 over log n chance of winning. You're definitely going to win. Okay, so what's okay? So you might have noticed this 1 over h looks a lot like something from last class, and that was this Galton-Watson tree. Okay, and this part I'll keep a little high level in the interest of time. But if you remember last time when we were doing those randomized min cuts, I imagine having a full binary tree, and then dropping each edge was probability 1/2, and say, what are the odds you survive, 10 generations, at least 1 in 10? Okay. What we're going to do is we're going to generalize from binary trees to k-ary trees. Okay. But I'll keep that like average degree 1-ish. Okay. So you have 100, children or something, each occurring was probability 1 over 100. Or each edge dropped is probability 1 over 100. And you can do basically the same proof we did last time. For some reason, h equals 3 is like a funny exception, but you're going to get the same thing as before, 1 over h. So I won't do it because it'll be the exact same proof, which just was that, 2 substitute was a generic k. Let's focus on trying to apply it. Okay, so it is true that, you could think of it as starting with a full tree and then dropping edges. You could also think of it as sort of a biologist would. At a particular time, you have some population, and then everybody who's alive is going to flip k coins. And if I flip 5 coins, I have 5 children and then I die. And something like this. Okay? Or flip 5 heads, I mean. So in other words, you can think of it as sort of an exploring process instead of like a full tree that's still leading things in hindsight. You'll get the same thing. Okay, so what I want to do is I want to connect our kind of searching algorithm with a Galton-Watson style process. It won't be the exact same. I want to show that the Galton-Watson process is sort of like more conservative than our search algorithm. Okay, so, and I'm only going to do it, not, I could be more formal than I am going to be, but I want to kind of somehow try to couple or relate them together. All right, so, okay. So the way we're going to think about it is like this. So V0 is like your root, okay? And then based on, V0, you're going to reveal as children, right? In that set A1. And then you're going to find, it has a couple of children or something. And that's like your set A1 or your set S1, right? And then I'm going to think of V1, you can think of, for example, doing our search in like a breadth first search order, right? So that'll be like V1 and then V2, something like this, okay? And I know that as long as I don't have, h vertices yet, there's n minus h vertices out there I'm sampling from, right? So like the maximum number of possible children is always like huge. Okay? So let me do this a little more slowly. So, okay, so remember the search algorithm. So my goal is just to get to h total vertices in my search. And I'm going to try to bound that below by the odds of a Galton-Watson process getting to generation h. Okay? And the way I'm going to think about like this, imagine after like 9 rounds, and assuming I haven't found h children yet, okay, then I'm going to be sampling from at least n minus h other vertices out there. Okay, which, yeah. Kept. Yeah, sorry, the average degree should be like 1. Or average number of children should be 1. What did I write? Oh, okay. Yeah, that's a big one. Okay. Yeah, the sad thing is I've done these slides for a couple of years. All right. Okay, so they should be kept with probability 1 over k. So as if you're going to get one child on average. That's sort of the critical point where this analysis is interesting. Okay, so if I'm at like A10, I don't have h children yet. I'm at round 10. Okay, then I'm sampling out of n minus h, which is still pretty close to n. It's at least n over 1 plus epsilon. Okay, and if I'm sampling with probability 1 plus epsilon over n, I'm expecting to get at least 1 vertex. Okay, so like that expected kind of branch factor is still at least one. Expect one offspring. Okay. So what happens then is that, at some level, like, okay. So kind of that Galton-Watson process with sort of average children one, surviving H generations is harder than just getting a total of H total children over the whole thing. So if you get down to H generations, then you definitely have H total vertices. But it could be easier if you're allowed to spread out your H vertices. Okay. And then getting to a total population size of H in this Galton-Watson process will be easier than our search algorithm exploring at least H vertices. Okay, because until it gets to H, we're still each vertex expected to spawn, at least one child. Okay, so I'm kind of coupling these things together. You could kind of do this a little more formally. But if you put this all together, then you'll find that, because exploring, for getting a connected component of size H is easier or more likely than getting a total population of size H in that kind of simulated process, which is easier than surviving a full H generation. If you survive full H generations, you definitely get a total population size of H, and that we know is 1 over H. Okay, so you can relate that together. So at some level, what's going on is that at a very small component, you basically don't have any redundancy among the explored vertices. So there's not that much difference between like a full kind of branching tree and this kind of randomly, potentially more connected graph. Okay, that's an appropriate amount of time given what's left. Let's quickly talk, so you guys can guess this, how to prove now that there will be a unique giant component. Okay, so what we've established is that there's no medium components. Okay, and then we've also established that there will be at least one giant component because you'll reach this critical threshold of log n over epsilon squared. Okay, and now you just want to show that there's going to be a unique one, which is kind of cool, right? All right, so here's what we're going to do. So the original process is based on the following, right? Where I sample every edge with probability P. But we're going to think of it differently. We're going to think of dividing the graph into two parts, each with n over 2 vertices. Okay? And you know that each of these, there's going to exist some giant components. Because that's just what we showed, right? Some giant components with high probability. So each of these will have at least epsilon n vertices. So imagine splitting the vertices in half and sampling their edges separately. And in each of them, they're going to get some giant components. We should note that there's at most 1 over epsilon giant components in each one because each giant component has size epsilon n. Okay? Now, I want to claim that we're almost definitely going to get, now we're going to sample the cross edges. And my claim is that between any pair of giant components, one from each side, I'm almost definitely going to get one edge. But why? Yeah, there's a lot of pairs. So there's epsilon squared over n squared possible edges, right? And if I start multiplying that by, roughly 1 over n, right? Now I'm going to get something like epsilon squared n. I'll leave out the 1 plus epsilon, right? So we're actually expecting a ton of edges in between them. And they're all independent, so you're definitely going to get at least one. Okay? So you're definitely going to get at least one. So in fact, they'll all be kind of connected across. And that'll connect everything to each other, right? So by the time you get some giant components, now it gets very easy to connect the giant components because they each have so many vertices and getting roughly n squared possible vertices, and you're expecting roughly n edges. So that's no problem. Okay, so that's how it all comes together. Some other class, if time permits, we'll do the proof of the Chernoff bound. It's been a tradition in this class to never get around to doing the proof, but we'll certainly get a lot of practice with it. The first most important thing is to kind of appreciate the qualitative nature of concentration. Okay, thank you.